Hi YouTube folks, this is Bamboozling Bit, and today I'm going to wrinkle your brain with some discrete math. So the problem of today is the poisoned wine bottles problem. Okay, so suppose you have 63,577 wine bottles, and you got a letter from a jester, no you're not Batman, you're a wine exporter, saying that one of the bottles contains a dose of cyanide that can kill 10 people, okay? You have to send out 63,377 bottles in an hour. Luckily, you own a lot of prisons and have 100 inmates in death row. Now, what is the main goal? Find a number that is greater than or equal to 1 or less than or equal to 100 that minimizes the loss of wine bottles and minimizes the number of deaths, okay? So we have 100 guests for the wine tasting. The Last Supper, okay? So basically, what's gonna happen here is that we're gonna use some modular logic to guess what is the number of, wine bottles that each inmate is gonna have to taste, okay? So for instance, we could divide this by 100, which means that 63,577 mod 100 is 77, okay? Now, what does this mean? It means that we're gonna have a certain number of inmates that are gonna drink only 635 wine bottles, and a number of inmates that will drink 636 wine bottles. So you have to guess that number.
What is 77 plus 33? 100!
Okay, people, so it turns out that 77 plus 23 is 100, as opposed to the popular belief that 77 plus 33 is equal to 100, okay? And turns out that 77 times 636 and 23 times 635 summed up equates to 63,577, okay? Now, in an ideal world, 7, 7, 7, 3, 3, 7 plus 3, 7 plus 3, 10, 10, 10 times 10, 100, I don't know. That seems like a weird arithmetic not, or arithmetic int, okay? But moving on, this means that if one of the inmates, let's say like inmate 77 dies, that means that 636 wine bottles will be dropped off, like going to the garbage because they might be poisoned, and the rest remain for use to export. However, we can only afford to lose 200. So this is a very bad deal, okay? Because they have to export 63,377 wine bottles, okay? Now let's just analyze what we have and what we can do, like, to get an optimal solution. There's 100 prisoners who will be invited to a wine tasting. Yum. Okay? A bottle can either be drank or not, so we have 2 states for each bottle, okay? Now, focusing on the 2 states of each bottle is key. Why? Because, for instance, we can start saying that if we have those bottles, we have 2 states, right? A prisoner can either drink it or not, and we can label it like that. So we can say like, yes, no, right? However, we can do the following. This is one solution. Maybe we can label the bottles with a 1 if a prisoner drank it and a 0 otherwise, okay? Notice that we can change the meaning of 1 and 0, but let's leave it as is. Like, for instance, we could say that 0 is drinking it and 1 is not drinking it, but for now, 1 is drinking a little bit of the wine bottle, okay? Now, what has to be noted is that 1 and 0 are the numbers that characterize base 2, okay? Thus, we can get the ceiling of the log 2 of 63,577 to determine the minimum number of prisoners that we need, okay? And you're gonna see that this is the minimum because there's only 2 things we can do with these bottles. Like, for instance, if nobody's gonna drink these bottles, then we don't care because we only have 1 state. We can just send them. It's like, oh, nobody's gonna drink them if we just say that every bottle has cyanide. But who would want to buy a bottle that has cyanide, okay? you want to drink your wine, you know. So essentially what you have is that you get the ceiling, and the ceiling of that value is going to be 16, okay? So we need 16 inmates, sweet 16. Okay, so let's go more thoroughly over it, like let's understand it. So, the bottle with 16 zeros was not tasted by a single prisoner, okay? In base 2, this is 0, but treated as the first bottle, okay? So for instance, if every single prisoner survives, guess what? The bottle with that label is poisoned, okay? Now, by that same logic, let's go with the one that has a 1 in here. You see this 1? This is index, the first index. So this is 1 in base 2, okay? So this means that the first prisoner tasted that bottle. If only the first prisoner dies, guess what? The second bottle is poisoned. And by that logic, okay? If this bottle that was only tasted by prisoner number 2 ended up only killing prisoner number 2, like prisoner number 2 is the only one that died, guess what? Then the bottle that represents the number 2 in base 2, which is actually the third bottle, is the poison bottle, okay? Now, the bottle with the label 1, 1, and then 14 zeros to the left was tasted by 2 prisoners, prisoner 1 and 2. Guess what? If these 2 prisoners die, it is bottle number 3, the one that is number 3 in base 2, which is the 4th bottle, which is poisoned, okay? Now, the bottle with this label right here, you see that we have a 1 in positions 16, 15, 14, 13, 12, 7, 5, and 4, right? And this is the number 63,576 in base 2. But it is the 63,577th bottle, okay? Why? Because we go from 0 to 63,576, okay? Now, suppose that prisoners 10, 6, 7, and 1 die, but the rest survive. This tells us which is the poisoned bottle. Now, what bottle do you think is the poisoned bottle, okay? So now, drum rolls. Yes, you guessed it, the answer is 609. All you have to do is get the position from 1 to 16, and where there is a 1, raise it to that number and subtract 1. If you want to omit the subtraction, you can just number the positions from 0 to 15, okay? Which is the case because the one that is in this position over here is raised to the power of 0, and the one that is in this position over here is which is actually position 6 is raised to the power of 5. Now this one in position 7 is raised to the power of 6, and this one in position 10 is raised to the power of 9, okay? And so on and so forth, because you can see that this is going to be 15, this is going to be 0, this ideally you have 1, 2, you have 3 in here, oh my god, you have 3, you go with 4, you go with 5, look at those beautiful numbers, 3 dots. So yeah, 609 in there. But you know, what if we want to like struck a better deal? Like, you know, the minimum of deaths that we can have is 0. Remember? If not a single prisoner dies, it means that the first bottle, the bottle that represents 0 in base 2, is the poisoned one. And that is optimal, you know? 0 deaths, and we only lose 1 bottle. That is a great deal.
Bitch, you make that deal?
I'd make that deal.
I don't blame you. Damn good deal.
Okay, so now we have to address the elephant in the room. What is the greatest number of inmates that commit die? Now, if you use the range from 0 to 63,576, how many inmates commit die? Well, there's a maximum of 15 inmates committing die, okay? And that is in the case in which the bottle that represents 32,676 in base 10 is poisoned, okay? Which means that it'll be the 32,677th bottle, okay? And that'll be it. So yeah, 15 like a quinceañera. Now, suppose the wine exporter is miserable, okay? He is a guy or a girl with a mission to make all inmates commit die, okay? If possible. In this case, the range of numbers will go from 1959 to 65,535, because in base 2, 65,535 means that there are ones in every single slot or bin available, okay? So basically, 16 ones means that 16 inmates tasted the bottle that represents 65,535, and we still have a range in which we can fit all 63,577 bottles, okay? So in that case, yes, there might be a maximum of 16 deaths, and that is how the number of deaths can be maximized with a higher probability, okay? And we're going to go over the statistical implications in perhaps a later video. But for now, just know that if you encounter yourself in this situation, just use a number that begins from 0 up to the number of bottles that you have minus 1, okay? Because that way you can actually have an optimal scenario in which you have to get rid of 1 bottle and in which there are 0 deaths, okay? Peace out.